Okay, here's the second lesson for Unit 9. And I just want to give you some information about this. Because of the calendar this year and where kind of breaks and conferences and everything fell, we're kind of cramming more into this lesson than we usually have. We're doing all three of these on one day is a bit ambitious. And on top of that, I hate to tell you this, but I have a sub on Thursday and Friday this week. So you're watching this video in preparation for the day there's going to be a sub there. So this video is going to be kind of long on the long side because I'm going to do more explaining than I usually do because of that sub situation. And then in class you will have some things to practice and do with the sub there. Okay, so this is areas of regular polygons, which was still in the area chapter, and then we actually start the 3D stuff today with prisms, cylinders, pyramids, and cones, which seems like a lot there, but I mean, I guess altogether it's kind of a lot, but the four figures for 3D are actually not that bad. Okay, so let's talk about circles and, regular polygons and composite figures. And I said circle because a lot of this is based on kind of the reasoning for a circle. Okay, regular polygon. We've talked about regular polygons before, but I don't think it was technically defined until now. They're equilateral and equiangular. So, yeah, you can have an equilateral hexagon that doesn't have all the same angles. Like maybe all these sides are the same, but the angles aren't. So, yeah, that the regular implies that it is not that all these angles are the same, which is kind of helpful. So, and they come up a lot in I hate to say real life, but they come up a lot in math problems, and they come up a lot in some of the 3D bases and things. So it's good to be familiar with those. Okay, so there's some terminology. This thing is called apothem. That is the term for, I don't know, you can think of that as like the radius of the inscribed circle. And I hate this, but they call this radius. They call it the radius of the hexagon. It's the distance from the center to the vertex. I don't know. I mean, I'm glad they talk about this right triangle because this right triangle is very important for lots of reasons. We're going to use it to basically cut the whole thing up into these right triangles, and we're going to use right triangles to find area because right triangles are very easy to find areas of, and all of these are going to be exactly the same. So it's all great, but the terminology just kind of bugs the heck out of me. Like, why do they use radius for something that's not a circle? Anyway, not our book wasn't the one that made that up. That's kind of standard geometry terminology. Apothem is probably the newest thing you haven't heard before. The central angle of a regular polygon has its vertex at the center of the polygon and its sides pass through consecutive vertices of the polygon. So they're saying a central angle. Okay, technically they're saying a central angle is an angle like this. They're saying this 60 degrees is a central angle. I don't think you're going to want to use that term very often. I don't think that term's going to come up very often. What we are really going to care about, if you think about right triangles and trig and where this is maybe going, is this angle right here, which is technically not the central angle. It's half of the central angle. In a hexagon, this would be 30 because I just had them all drawn here. There were 12 of those that went around the whole, the center of the polygon. Or you can think, of those central angles that we just drew. If it's a hexagon, there's 6 of those. And so, yeah, that's 60, and each one of those is going to be cut in half to make the right triangle. So it doesn't take long to figure that out. You'll get used to, regular hexagon is 30, and what the other ones are pretty quickly. And then, if you've got all that figured out, and it's based on those kinds of things, the area of the regular polygon is half AP, half times the length of the apothem times the perimeter of the whole thing. And I will discuss in class the why of that. It's not, I think they kind of explain it here, but it's not that hard to explain in class, and it's kind of based on one of the whys behind why the circle is the way it is. Okay, so we're saying find the regular hexagon if apothem is 8. So pretend that was 8. The area formula we're going to be using here is half times A times P, which is half times A. Now, okay, they didn't tell me about the side length of the hexagon, or they didn't tell me about AH or anything like that. But I can figure that out based on the fact that I know it's a hexagon, because in hexagons we have this special. Okay, they told me this. We have this special kind of size here where I know that's exactly 30. So this is the 30, 60, 90. I'm kind of interested in this because I need to know the perimeter of the hexagon, and that x came from this length right here, and that helps me find half a side. But this is a 30, 60, 90 triangle. This isn't too bad. If that's 8, this side, if you think about it, is from your special right triangles, is just 8 divided by the square root of 3. So the side of the hexagon is 2 of those. Whoops, square root of 3. And the perimeter of the hexagon is just going to be 6 of those. I need my calculator out again. That's just 96 divided by the square root of 3, which is just 32 times the square root of 3. That's the perimeter of the whole thing. So I did all that to find perimeter, and again, those will come faster to you. Why do I have an A over here? I already wrote that formula. Let's do this again. This is half times A times P. So this is the formula in variables. This is those variables replaced with values, and then that whole thing equals. But I guess I don't need the approximate equal. The actual equal 128 root 3. And if you want to put that as a decimal, it is times root 3. I'm on my calculator on another device. It's 221.703. And this is area, so I got to do units squared again. Okay. Find the area of a regular pentagon with a radius of 20. I think I should do this, again, because I'm not going to be there in class, and pentagons are slightly different. So if I draw apothem and I draw, also they gave me radius this time, and I draw that radius there, what's different about the pentagon is there's only 10 of these little right triangles in here instead of 12. So if I want to find that angle in there, I have to take 360 divided by 10. So that little angle in there is 36. It says radius of 20. I'm trying to find area. Yeah. And the formula that I care about is half AP, half times, okay, I don't have A and I don't have P. So I got to find that stuff. Well, this was 20. This angle is 36. So to find this apothem over here, here's another problem. Apothem starts with A, and when you're doing SOHCAHTOA, adjacent starts with A. So if we're talking about this angle and adjacent, and using the letter A, it's fine. But if you ever have to use this angle down here, things start to get a little wonky. All right, so with 20 and A, I think I'm talking about the cosine of 36 equals adjacent over hypotenuse. That's great. And yeah, hypotenuse starts with H, and so does the word height. And the H in all of these area formulas is not usually a hypotenuse, so that's a little bit confusing. Oh, that got really small when I did that. Okay, so apothem is 20 times the cosine of 36, and then perimeter. Sorry, that was helping me find apothem, and then from perimeter, I always call this thing x. X is going to be involved with sine. So x is going to equal 20 cosine 36. I guess to complete this, I should have said this. A is going to equal 20 cosine 36. Remember saying last video that cosine sine in the same, cosine sine in the same, I was thinking about that other one. Cosine sine in the same area formula happens a lot. Okay, so that's x. So the perimeter is actually 10 of these, because that's half a side. So the perimeter is actually 200. If you can still see that, it's 10 times this number down here. So 200. Why is my pencil so thin again? 200. Don't know why. Still reads the same. Sine 36. So to kind of 36. Kind of rearrange this so things are a little bit nicer, or to kind of simplify this first might be kind of nice. 200 times half is 100 times 20 is 2,000. Cosine sine, which on the calculator as a decimal is 951. I try not to be too mean about that on quizzes and tests if you make that kind of mistake. You may notice, actually, if you hit this and you hit equals in your calculator, enter in your calculator, and your calculator sent to exact mode, it actually turns out with pentagons, a lot of these regular angles associated with regular polygons, that this cosine 36 comes out to have an exact value that involves the square root of 5 and things. So there's an exact expression for this thing that's actually kind of a monster. Maybe I shouldn't even waste time with this right now, but you get something, my calculator shows me something like this. And then there's a square root negative 2 times root 5 minus 5. I mean, that's true. We never learned why that is. It's kind of crazy. So you don't have to ever use that expression. We don't talk about why. We actually talk about why that is in AT geometry if you ever want to take that class. But for now, because weird, my pencil widths are different in this problem. There's no reason for you to talk about. Oh, stick again. To talk about that answer when you express your answers for me. Just give me either the full-on exact values using the trig things, or give me a decimalized version of that. Okay, find the area of the equilateral triangle, which is the same thing as a regular triangle. So all the stuff we've just said about apothem and perimeter, that applies to triangles also, equilateral triangles. If the radius of its inscribed circle is 3, I'm going to draw this here because that should make us realize that that's actually the same thing as apothem. All right, if that's 3, here's that same kind of triangle I've been drawing all day, like that one. Okay, find the area of the equilateral triangle. We can use, believe it or not, I could use half times base times height, but I'm just going to show you here that you can use this for even triangles. You can use it for squares. Those are also regular. Those are the only quadrilaterals you can use it for. All right, so half, because what's kind of nice about this, the way it's given, I already have half of them. I just need to find perimeter now. Well, this is a 30, 60, 90 triangle, so that's 3 root 3. So the perimeter is just 6 of those things, which is going to be 18 root 3. So that's actually pretty quick to do it that way. Be my guest. If you want to do base times height, fine. You can find this height pretty quickly, and you can find, I mean, I just found base. It's 6 root 3. I guess it's not a whole lot quicker to do it any other way. That was about the same. So this is 9 times 27 root 3. I don't really, do I need to do this as a decimal? I guess I can. I've been doing that all day. I'll do it here too. 27 root 3, I get 46.765. We may actually ask you in some of these questions, just to make sure you can use your calculator, we may actually ask you to express some of these in decimals. Yeah, because that's a skill. And sometimes, you know, if you're building a shed, you want to know what that area is. It was the area of the whole rectangle, okay, or whole triangle. Yeah, because it reminded me of a similar figure from the last video. Okay, we still got a ways to go. Sorry, this is going to be long. Find the area of the octagon. It's inscribed in the circle with radius 12. Okay, so this is the 12. This is apothem. I got to think about this angle because I'm going to need to find x because that's involved in my ingredients needed to make this work. Actually, this isn't that much different than one we've done already today, so I am going to save that for your activities in class with the sub. Okay, that'll save some time. Composite figure. Okay, so this is a different section of the geometry book. Oh, no, it's not. I'm sorry, it's not. It's still part of the same one with regular stuff. But composite figure is not anything to be too terribly concerned about. It just basically means that, you know, you've got some weird thing here we don't have a formula for, but you know what? It's pretty easy to break down. I can cut it in 2 pieces and I can tell what the areas of those things are. So guess what? You can add them. So it's not like, yeah, you're going to have too much trouble with that, I don't think. Okay, find the area of these things. That one's a trapezoid and a triangle. This one's kind of insane. Maybe we'll do that one. This is a triangle and a rhombus. This is just a whole bunch of trapezoids and rectangles. Actually, none of these are particularly hard. I'll do the 2 interesting ones. I'll do B and maybe E. Yeah, I'll do B and E. I think those are the ones that I can lend the most value to here. And then we'll save, let me mark this. We'll save that one and that one for your in-class activities. Okay. So let me do this one. Find the area of this monstrous thing. Okay, so one way to do this is to find, kind of as a corollary to this postulate, I could find the area of this whole thing by taking trapezoid plus triangle. Like, that's not bad. But I could also find the areas of things here by taking trapezoid, if you see what I mean about this one, minus that little triangle in the middle. I could take the full trapezoid and basically cut out this triangle. Those types of things are also possible. So what I want you to do when you do quizzes and tests for me on these is give me your plan, kind of, and I kind of did this on the last video. Area of, like, some kind of subscript. It could be actually a little sketch is fine. Minus area of triangle. Actually, this will look a little more, because it's like, which triangle are you talking about? I'm talking about the triangle that kind of looks like that. Is the area that I want. Call that A. That's the answer to the question. And I thought to do that because it seems like I have most of what I need for both those things. I'm going to have to find this little length to here for both the area of the triangle and the area of the trapezoid anyway, so it's not like it makes it any easier or harder for me if I make those instructions. So let's talk about the ingredients needed for these. Minus half base times height. Okay, as soon as you do this, you got to realize a couple of things. This height is different from this height, right? This is the height involved in the triangle, and this is the height involved in the trapezoid. Trapezoid, triangle. We got to keep those things separate. Okay, so I gotta find blue H. Anyway, I think that's gonna be easy to find first, and then green H is just gonna be that plus 1. So to find blue H here, I know each one of these is 1. That's a right angle, the way I've got it kind of set up there. This is simply going to be from Pythagorean theorem. This is going to be the square root of 6 squared minus 1 squared. Remember, 6 is the hypotenuse. This is the square root of 35. That's kind of horrible, but it's okay. We can deal with it. So I can fill in some things now. This is going to be square root of 35. I'll leave that in blue. This green one, though, is going to be square root of 35 plus 1. Ouch. We are a long ways from being done. Okay, back to red. Minus half. What's the base of that thing? I think it was 2. That's not so bad. The bases on the trapezoid, so I still got the half here. The bases on the trapezoid are 12 and 8. I get this 12 here. That's 12. 12 plus 8. Okay, so I'm doing okay. This is going to be 10 times, whoops, that's too big. That's what I meant to do. 35 plus 1 minus root 35. Oh, there's some like terms here. 10 root 35 plus 10 minus root 35. That's just 9 root 35 plus 10. You can make it decimal if you want. I'm already conscious of time. I think the value of that problem is done. All right, here's another one where I think subtraction is kind of smart. And you know what? This is trapezoid minus triangle anyway. Yeah, maybe I don't want to do this one. Maybe you could save this for class 2. Okay, let's get on with the 3D stuff. Okay, is there anything, okay, now that I said that, is there any of these I really want to do? Trapezoids, triangles, All right, I think you get the theme. There's a lot of trapezoids and triangles. Okay, now we're finally on the next section. This is now 3D coming from here on. Okay, so we have, I think prism is the first thing that I should talk about here. Prism is a polyhedron with 2 parallel congruent bases. That's kind of a big statement. In class, when I get back, I'll be able to show you. I have a lot of models for these things. And basically, the two main categories of things we're going to be talking about for most of this unit is there's things that we call prisms and there's things that we call pyramids. And I think you probably have a pretty good idea of those of what those are. But prism is defined as we have some parallel faces here that are congruent. So like in this prism, we have this face up here and this face down here, and those are congruent parallel hexagons. And they're all joined with these rectangles. There's actually 6 rectangles that join the two together. So when that's going on, that's called a prism. So there's the things that were called the bases, then those hexagons. Those rectangles that join the bases of a prism, those are called the lateral faces. And they have lateral edges. There'll be like edges like this. These are the lateral edges. They're labeled in this picture. And base edges are the edges like, the edges that, the edges that come along the side like that. Those are lateral edges. So if I erase all my writing here, you probably see the labels better. Wait, how come I can't erase everything? That's interesting. Not gonna worry about it. But on your printed one, you'll see that maybe better. This one's called a right prism because it's standing straight up. This one is called an oblique prism because it's not. They've indicated there's a right angle, and things are kind of slanted over. We don't deal with we call oblique prisms very often. There are some formulas we're going to derive that do apply to both, and there are some formulas we apply that we derive and work with it only apply to right prisms, so I guess pay attention to that. But generally speaking, the volume stuff is really easy. Volume is gonna kind of apply to both, but when we start doing surface area, that's only going to apply to this one. And we're not going to talk about surface area for that because it's really a nightmare. Generally speaking, volume is a whole lot easier to deal with than surface area. But we're trying to talk about surface area first. Okay. Because we've already talked about area, because it connects already to what we've been doing, so that's why. So the lateral area, we just talked about bases and lateral stuff. So remember, the bases are these parallel congruent things, and then the rest of the wrapping there, all the standing up rectangles, those are what's known as the lateral faces. So when we talk about total surface area, there's formulas that make it easy if we break that up into finding the bases and finding the lateral area, because the lateral area can all be found in one step instead of finding all these steps. Because you could just find all the separate rectangles, fine, but there's a shortcut here for the lateral area. Basically, what that is, and this is a triangular prism. This is not a pyramid. This has 2 congruent faces that are triangles and they're parallel. Everything else is a rectangle. And if you were to unwrap this, you could realize that all those rectangles could be laid out like this and it would form one giant rectangle. And that one giant rectangle is easy to deal with because it has the same height as the original rectangle. But then if you think about this whole thing, that's just this triangle unwrapped. This is the perimeter of the triangle. So, the lateral area is the sum of all these lateral faces, but that's really just a rectangle where the one side of it's going to be the perimeter of the base. That's where that came from, and the other side's going to be the height. Great. So that's lateral area of the prism. Then the total surface area of the prism is just take that lateral area and add on the triangles. Oops, I had a timer going off. Sorry. Okay, let's keep going. And we'll do some examples in the later parts. What if that, instead of being a regular polygon or being a square or being a rectangle on the bases, what if it was a circle? Well, life isn't too different. This belongs kind of in the same category as prisms. There's an axis. We're not really going to, well, I guess we'll deal with the axis a little bit because that helps us. The axis is what helps us tell the difference if it's right or oblique. Again, we're not going to deal with oblique as much as we're going to deal with right, but that's what they're called, and that's, I guess you need to know they're there. Volume is easy, surface area is hard. But yeah, if you were to think about what happens with the lateral area now, lateral area is still a rectangle. The height is still the height, and now this edge of this rectangle is what we would think of as the perimeter of the base, but now we just call that circumference. So lateral area is 2 pi r h, because it's this circumference times height, 2 pi r h, and then the total surface area is just take that and add on the two circles, 2 pi r squared. All right, so now we're going to actually try to do something. Okay, so lateral area. The formula I need is lateral area equals pH. That looks like a laugh. Okay. All right, this one is a pentagonal prism. The way they've drawn it here, it's not sitting on the base. The base is kind of staring us at the face, and then staring us in the face, and the other base is kind of the one in the back there, which may or may not be easy for you to see. So the height of this prism is actually 4. The height is, and you can think of the height as being defined as the distance between those two parallel congruent faces. And this 8 being here tells us if it's a regular pentagon, all the faces of the pentagon are 8. So I just need perimeter times height. Perimeter is easy. That's just 8 times 5, which is 40. And height is 4, so life is easy if you can multiply. 160. Surface area. Surface area is going to be lateral area plus 2 bases. This is where it gets tricky. So this is 160 plus 2 times, and we know this is a regular pentagon, so from earlier, we know this is half AP. So this isn't crazy that I put this on the same day. Okay, which is another way to say this is 160 plus A times P, and P we already figured out for the other thing, it was 40. Okay, so the trickiest thing on here is going to be apthem. So I usually like to draw the base flat and just looking right at me, so I can think about what these things look like. Okay, and what do I know about this? I just know that the side length is 8. So in other words, this part's 4, and I need to find apothem. But I know what this angle is. This angle is 1/10 of 360 because it's a pentagon. So pentagon has 10 of those little triangles in there. So the trig function I need here is tangent. Tangent of 36 is opposite over adjacent, so 4 over tan 36 is what A is. Okay, well, gosh, that got really small again. So this is 160 plus 4 over tan 36 times 40, which is something like, I mean, there's the best exact way to say this, 380.221 units squared. Because that's still even we're talking about 3D, we're still talking about surface area, so that's still in square units. Lateral area, surface area of, I guess I should do this. Lateral area and surface area of the cylinder. Lateral area is perimeter times height. I know in the formulas up here for a cylinder, they said lateral area is 2 pi r h, but really this is just circumference of the thing, which you can still think of as perimeter, and it's not totally wrong. And I think conceptually that's less things to memorize, so, or internalize. So I would just leave it like that. All right, so lateral area is perimeter times height. Perimeter here is 2 pi r times h, so I just kind of expanded that a little bit. 2 pi times radius times height, which is just 30 pi. And this is in area, so we're still in units squared. Surface area is lateral area plus 2 bases. Lateral area I just figured out. 2 times the base area, which is, base areas here are pi r squared. This is plus 30 pi plus 2 pi times the radius squared, which is 30 pi plus 18 pi, which is 48 pi. I'm not going to make that a decimal. Feel free to do that. Given a right prism with a height of 12 and a regular triangular base with an area of 18 root 3, find lateral. Yeah, that's a class one. That's totally fine. Okay. Yeah, because I know we're getting on the long side. This prism, okay, this is kind of a weird composite thing, so this does kind of connect to the earlier thing from today too. Find lateral area, find surface area. Okay, so we're going to call this a prism. They're calling this a singular prism. So they mean this is the base, it's congruent and parallel to this face in the back, which is like this, and we can use the formulas that we've been using so far to do this. Okay, so lateral area It's going to be perimeter times height. And again, height is defined to be the distance between the parallel congruent faces. So we need to know the perimeter of this trapezoid. So we're going to call it trapezoidal prism. I should have written that here when I said that. It's a trapezoidal prism. Okay, so the height is 25. That's easy. But the perimeter is going to be a little bit tricky. All right, so is this working now? Oh, it is. Okay. That was kind of in my way. So can I get the sides of this already? Because that's 16. That's great. This is a 45, 45, 90. So I know that this part has to equal this part. I believe. Oh, and they tell me this is 7. This is 7. This is 7. This is 7. Wait a second. Oh, no, that doesn't have to be 7. I'm sorry. I messed that up. That's not going to work, is it? If that's 7, then I know this is 7. Sorry. And so this part has to be 9. Because the whole thing has up to 16. And these are equal because it's 45. 45, 45, 90. Okay, so that's a 7 by 9 rectangle kind of thing there. So the perimeter is 16 plus 9 plus 7 plus this. Okay, so that's 7 plus 9 plus 7 plus 9 on perimeter. Plus this side, which would be 9 times the square root of 2. Yuck. So that's 32. The perimeter is 32 plus 9 root 2. But the height is just 25. So in my calculator, 32 plus 9 root 2 whole thing times 25 gives me, I want to expand that. 225 root 2 after 800. 800 plus 225 root 2. Decimalize that if you wish. Not a bad idea. This is 1118.198 units squared. And then surface area is just going to equal that plus both bases. So that's 800 plus 225 root 2 plus 2 times these trapezoids. And remember, h is not this h. This h is height of the trapezoid, because we're trying to find area of a trapezoid here. So height of the trapezoid and height of the prism, those are different heights. Be careful. Okay, so back to this. We have 800 plus 225 root 2 plus, I'm just going to cancel the 2 and the half. Base 1 here is 16. Base 2, that's this. Base 2 is 7. That's this. Times height, which I have, which is 9. 23 times 9 is not bad. 23 times 9 is 207. So I'm just going to add that to the 800 and call that 1007 plus 225 root 2. 1007 plus 225 root 2 as a decimal is 13. And I hopefully, yeah, this is supposed to be bigger than my last answer, right? Because I've added things to it. And there we go. Okay, given a right decagonal prism with a height of 8 and apothym radius, blah, blah, blah. I think we can do that in class. Great. Okay, how much of this is left? Oh, we have to do pyramids. That'll be the last major concept, I believe. All right, pyramid is, you see some pictured there. Instead of having the two parallel congruent faces, this just really has one base. And then from that, we have triangles that lead up to a vertex. So in this first picture you see here, we have a square base, which is very popular for these things if you go to Egypt. And then all of these triangles that lead up to it, they're all congruent isosceles triangle, and they lead up to this one thing called the vertex. This one's standing straight up because this altitude excuse me, is a segment that's perpendicular to that flat base. Here it's not. It's perpendicular to the flat base, but it's not the center of the square. So if it's right over the center, like, center of gravity kind of, and this vertex is standing right over the middle of the base, then we call it regular pyramid. This is oblique or non-regular. Yeah, we can still find, and it's just like what I said about obliques. We can find everything about this pretty easily. On this one, we can find maybe volume, but that's about it. Surface area is kind of a pain. I think I went through all of the terms. We still have terms like lateral faces and lateral area, but here, lateral faces are triangles. If it's regular, they're going to be isosceles triangles. These are going to be isosceles triangles. And lateral area is going to be the sum of all those triangles kind of around that figure. Height, altitude, that's all kind of stuff I already talked about. Okay, so for regular pyramids, here's some things to remember. If they say regular pyramid, that implies a lot of things. First of all, the base is a regular polygon. And the thing is standing straight up. That also means it's standing straight up over the center. So it's like also a right pyramid. Yeah, they're all congruent isosceles triangles. All the lateral edges. So this is a lateral edge. All these lateral edges are congruent because again they're all congruent triangles standing up like that. So that makes it very easy to deal with. I guess the newest term here is the term slant height, which was way back here somewhere. Yeah, they had slant height labeled on this a long time ago. Slant height is this segment here, which goes. So remember we were talking about how all those lateral faces are congruent. You think about the lateral area now. The lateral area is like 4 of these congruent isosceles triangles, and we're going to want to find the area of these isosceles triangles, so we're going to need to know the height of the triangle. So this is like if you're walking up the side of the pyramid, you'd be walking up that green thing. This red thing in the middle is shorter. That's like if you're taking an elevator up to the top of the pyramid. This one's more like if you're taking the escalator up to the top of the pyramid, and it's longer. So the escalator one is the slant height, and that's the one we're going to need to calculate the area of those faces. The red height is called altitude, and we need it for volume. So we need both of those. And the other thing, and I have it in here a lot, is we have this little triangle that shows up a lot in the middle of the thing. Sometimes I call that the HAL triangle because the height here, this is the red height from before. That's the elevator height. Here's the escalator height. Yeah, and then the other thing is the one on the floor here, which is called apothem, which we just did in the regular polygon stuff. And that would be apothem if this was a pentagon or a hexagon or whatever. So this triangle in the middle is going to be very important. We're going to use it to do Pythagorean theorem to find missing ones if we only have some of those and that kind of thing. So that's an important triangle to imagine in all these pyramids. Okay, lateral area. The formula for lateral area, if you add up those isosceles triangle, is going to be 1/2 times P times L. And it's the same. Oh, by the way, slant height is L. This... Can I just continue with this video? I accidentally saved in the middle. I hope this is just going to continue. The slant height is known as L. We use the letter L for that. And so the L is the height of those triangles. So this 1/2 PL comes from the idea that we're doing 1/2 times base times height times all the triangles, kind of like that, or times. Sorry, I shouldn't have said height, right? I should have said L. And then we have this multiple times. So instead of using base, they add up all the bases and call that perimeter, and that will account for all of the triangles. So that's where we get 1/2 PL. I usually say 1/2 LP. I don't know why I learned it in that order, but I usually do. You'll hear me say 1/2 LP. Then when we go to do total surface area, the difference here is there's now only one of these bases to add because it's a pyramid. And pyramids are going to only have one base on the bottom. We added 2 when we did prisms because there were 2 bases, and there's just only one on a pyramid, so we don't have to add it once. Okay, and then let's also take this and apply it to cones. Cone still has a thing called the slant height. It still has a thing called the regular altitude kind of thing. There's still this right triangle, but now instead of thinking of apothem, we can just think of radius. That makes a nice right triangle, and life is good. Yeah, so 1/2 LP here, if you're thinking about how the, it's down here. If you know how the surface area applies to the lateral area of a cone, 1/2 slant height fine, but perimeter we can kind of think of as 2 pi r. So sometimes you see this simplified. They have it down here as pi r l because the 1/2 and the 2 cancel, and people write it that way. So that one, there's a little bit of advantage learning it that way, but if you just remember 1/2 LP and that P is still the circumference, you're not going to get this wrong. Here's a picture of a cone taken apart, and if you were to take like a paper cup and cut up a side, it's going to look something like this. And this edge, as you stitch it back together, this kind of huge arc is going to wrap perfectly around this circle, which represents the base. So those are the same length, always, if you're going to take a cone apart. Okay, let's just do a couple things here. Okay, given the regular pentagonal prism, find lateral area and surface area. I kind of hate those numbers. Can we do a different one? Yeah, this is a little more typical, I think. All right, given the regular square pyramid with base edges of 10, what's this? A lateral edge of 13. Okay, lateral edge, notice, is in none of the formulas. So this is kind of interesting because it's going to make us do some algebra acrobatics to get what we need. This one's a little better. So find slant height. So that's L. And L is, I keep using L as this green line, so I'm going to make it green again. And this is part of a right triangle also. This right triangle is on the surface of the pyramid, and it is a right triangle. Remember that L is like the altitude of the of the face of the pyramid. If these edges are 10, each one of these is 5, because it's an isosceles triangle. I know that it's got that symmetry. So with Pythagorean theorem, pretty quick, I figured out that that's 12. 12 squared plus 5 squared is 13 squared. So L is 12. Lovely. The altitude, which we're talking about as H, that's part of a different right triangle. This is also 5 because it's part of a square, and that's the apothemenus square, because this would be a 45-45 triangle on the 45-45-90 triangle on the floor there. But now I have the HAL triangle. The HAL triangle has this is 5, this is 12, and I gotta find this. So I do Pythagorean theorem again. I get 144 minus 25. This is the square root of 119. All right, and then lateral area. Lateral area here is going to equal, it's not perimeter times height, it's half LP. And I know L, and I know P. So this is just 20 times 12. I'm actually not going to trust myself. That's 240. Total surface area, I would just have to add on 100. So that's not so bad. Let's do a round one. Let's do a cylinder. Lateral area is supposed to be half LP, or if you're fancy, you can remember that it's pi r L for a cone. Because P is just 2 pi r, and then things cancel. Radius is 3. Slant height is, I don't know. Slant height is this thing. There's a right triangle. There's a 10 and a 3. So this is the square root of 109. Is that right? 100 plus 9. Yep. 109. And I'm just going to leave it like that. 3 pi root 109 is the order I like to see that in. And then surface area is just lateral area plus a base, which is 3 pi root 109 plus pi r squared. Notice there's only one of those here because there's only one of these circles. And that circle has an area of 9 pi because it's pi r squared. There's really no way to simplify that, so I'm just going to leave it like that. Okay, I'm going to stop there. I'm going to remind myself that these are the ones we need to do in class. We're going to do this number 4, and we're going to do this number 1. Okay, and I put this little note here again. Stop here. Don't do this. We're going to do this in class next time. You're going to do it with the sub, and you'll have some other things that you can practice with the sub. Sorry this was so long, but that's just the nature of where we are in the calendar right now. Thank you.